I was very happy with the homework situation. That was very good. Thoughts on the homework? I'll review from Chem 1 as far as I'm concerned, but y'all tell me how was it? Yeah? You feel like you could do that successfully all the time? Maybe that thing we started live with Monday now feels a little easier after brushing some of that stuff off. Yeah? The balancing go okay? Balancing those equations? Maybe. You'll see on one of them particularly, I noticed on the phosphate one, I noticed in balancing that PO4 stayed together, right, on both sides of the equation, right? So I just treated PO4 as a thing instead of balancing the phosphorus, the P, and the oxygens separately. I just balanced it with the PO4. Another one, maybe two of them, I balanced with fractions. A lot of times, like one of them I balanced with 1/2 O2. If you balanced it the other way around where you double everything else, that also works. They get the same answer. Okay. But let me encourage you to not fear the fractions. I did a lot of the fractions when I was balancing equations in geology. It's kind of the norm there. Chemistry, it's less so. Chemistry, they usually like for you to do it with whole numbers. But, Miriam, I think you said this to me, that the answers are like, well, yes, but no, or this, I had to give you a thing and then didn't tell you no, and that's never mind. I change things later. Yeah. Well, so chemistry does that with balancing equations. So they'll balance with all whole numbers, and then we'll get to thermodynamics and electrochemistry in section 4 of this course. And then even your book starts balancing with fractions because it makes things easier. So if you concentrate on certain things being whole numbers and let other things just be fractions again. So we'll deal with that, but maybe practice balancing with fractions sometimes to see. And if you need help with fractions, I can help some, but remember the people in the math lab are experts at helping you. Okay? How do you feel about the fraction balancing? She does it either way. Okay. So section unit 1 of this course is gas laws and phase change stuff. Then unit 2 we'll get into equilibrium and more of what I think is more fun stuff later. But so we'll start out here with the gas laws, and I have several things that I want to ask you about this. Notice, this is a table from your textbook, common gases in chemistry. I always just like this. You look at the periodic table here, you know the colors, what they're trying to show with the different colors here? You see the color? You got black, you have blue, red, and then you got these outlines. You know what those mean on the periodic table? What? Which ones are? Yeah, that's what they're trying to show. So the red ones are like gases, the black ones are solids, the blue ones, what do you think? Liquids. What about the outlines? Not naturally occurring. So everything past uranium, although there's a brand new study from a year and a half ago which calls it a question of plutonium, but for the most part, everything after uranium is not naturally occurring. We made it in a lab, synthetic. So that's why they make those outlines. Anyway, the part that bothers me about this is, well, nitrogen is a gas, except when it isn't. We've got liquid nitrogen upstairs, right? So I don't like that we make it that hard-coded. It depends on the conditions, the pressure and temperature, right? Maybe some other conditions that we'll get to later. So I think it can be a little misleading, but you see what they're going for. Those are typical gases, right? I would mention, look, H2O. H2O is not listed, but certainly H2O can be a gas, right? You have steam, that's an H2O gas. Yeah. All right, well, tell me when I'm talking about a gas. What do you think of when you think of a gas? Give me some description. If you say, this is a gas, and he says, no, it isn't, what are gonna be the things you talk about back and forth to decide who's right, whether it's a gas or not? What are you gonna, what things? What could convince you whether something is a gas? But, okay, he's like, yeah, but I can't see that. Anyway, where would you draw the line? Like, how excited is gas excited and how excited is not gas excited? Okay. What else? Why you say it's not a gas? I don't know. I don't know what the thing is yet, so why would you say it's not a gas? Anybody watch Star Trek? Star Trek shows, okay, we're watching Star Trek Discovery, like, later seasons right now. So we're out in spacecraft and we're in a new mission. Oh, it's a gas cloud, right? Wait. Why do you say it's a gas? What makes it gas? Okay, we're in space in that case, but okay, so what causes something to float? Let's think physics. Okay, so can I have a gas that sinks? Right, can you think of an example of one? Any history, anybody like World War I history? Okay, what was the big technological invention in the trench warfare in World War I? Heavier than air gas. Was a gas though, right? But it sank and it would drop down into the trenches. Chemical warfare. What else? What else could you think of? So it doesn't always float. What else? What would you say? Oh, now wait, if I can do this, it's not a gas. Oh, okay. So maybe if you could just pick it up and hold it in your hand. Okay, yeah, that's a good idea. Keep thinking on that. We're going to come back to that with phase changes, which is week 2 or 3? Next week, anyway. We'll talk more about the properties of it, but start thinking about that. It's also, there's some information in your textbook about that. What states of matter, back in high school, what states of matter did they talk to you about? What do you know about? Maybe middle school. What do you already know about? Solid, liquid, gas. Do you know a fourth common one? Okay, what is plasma? And so one of the things I wanted to clear up really quickly, because there's a really common misconception about plasma. So, solid, liquid, gas, plasma, where's plasma at in relation to those other 3? Say it again?
Faster moving than gas.
It's an even higher energy than all 3 of the others. So you go energy ranking, you go solid, more energy, liquid, more energy, gas, even more energy, plasma. Okay? It's basically an ionized gas. It is a gas that will conduct electricity. So if you have the electronic group on the other side. There are a lot more states of matter than that. There's some arguments about how many we want to call states of matter, maybe 17, maybe 23. But these are the 3, and then maybe the 4th one that you'll deal with in undergraduate. All right, let's see what else. Another thing that I will say, and we'll talk about this more next week. A lot of times the term state of matter and another similar term, phase of matter, are used interchangeably. And next week that's going to change for us. Those 2 things are going to have a different meaning. Phase and state. Okay, so just know that that's not. All right, characteristics of gases. So this is what I was looking for. Is what do we look for a gas? Well, they'll assume the volume and shape of the container. So you can move. You can change the shape of a gas, right? Like so. Right now this is full of my coffee, but actually no, it's not full anymore. But when this is empty and it's just full of air, right? The shape of that air in here is whatever the shape of the container is, right? Or you could do this with a bigger container, like the shape of the gas in this room. It's the shape of the room. takes the shape of its container. Does that make sense? Okay. And whatever volume. Here's the big deal though, is that they are compressible. So what does this term probably mean? Take the word apart. Be brave. Give it a guess. Any ideas? It can be squeezed. I like squeeze. That works. It can be squeezed, and the volume can be lowered. You can compress it into a smaller volume. Okay, and that's really where we're going to be with today's gas cells. Okay. Also, a big thing about them is that they will mix evenly when they're confined to the same container. Liquids don't always do that. All right, like your salad dressing with oil and vinegar salad dressing, right? Doesn't just stay mixed evenly. Some liquids do, and some don't. We'll get to that when we get to solubility. And they tend to have much lower densities. I think this is where you were going earlier with the floating, right? They do tend to have lower densities than liquids and solids do. Okay? But again, that's not always a hard and fast rule. Okay? All right. Let's see. So one of the things I pointed out on Monday was that dimensional analysis stuff, all the unit canceling that Dr. Shim talked about, right? So that stuff's coming back right now. So let's dig into this. Who has had, let's go first, who has had college level physics? No one, 0. Okay, so that's the thing to think of. Who had high school level, there's a little bit of a problem with that. Who had high school senior level physics? You did? Yeah. Okay, so a few. Anybody else have a class in high school that they called physics? What year?
It was our junior.
Junior year. That's probably similar then to the senior one, right? Okay. All right. There was a move to move some of it to freshman year. When did you have it? Freshman year. Okay, so I think that course is probably drastically different because of the amount of math that you have, right? Because physics is like all that up with math. Okay. So let's dig in. This will be a little bit of physics. This whole unit is a lot of physics, really. Okay. So let's dig into this. All right. So pressure is this thing defined as force divided by area. Anybody do any off-roading type stuff? Yeah. What are you driving? Oh, okay. Motorcycle off-roading. All right. That's interesting. That's new for me. That's a different one. Let's say we're out. What are you driving? What do you got? What are you riding? All right, he's got his Kawasaki 250 out, okay? So he and I are out there, we're about to go across some mud, okay? He's on his Kawasaki, and I'm in my Wrangler, my Jeep Wrangler, okay? So as we go across that, are we going to sink in the mud the same amount? What do you think? Right. Brianna says no. Why, Brianna? Okay, so which one's heavier? His motorcycle or my Jeep Wrangler? The Wrangler is definitely more mass. It is definitely heavier, but yeah, you're going the right way. Keep going. She gave you the key already, so somebody kind of like jump in there with where she just, because she already spoiled the answer. Yeah, go ahead.
Just a surface area. So
She did.
for the motorcycle, the mass is distributed less, so it'll sink faster.
Yeah, but how wide are your tires?
Very average.
Yeah, so my Jeep tires right now are 1150s, so they're 11 and a half inches wide, right, 33s, so, right? So even though there's more force, more weight, you are absolutely right, the area that is distributed across means the Jeep puts less pressure on the mud. that a motorcycle does, right? What's the motorcycle like?
There's a way through?
Yeah, what's y'all's norm?
They just up and down. They just
But I mean, like, if you're in, like, if you get some slimy mud, what do you usually do? You're sinking.
stay it.
Yeah. I mean, that's not different. So roommate in college had a Jeep, but he had been a tank driver in the Army. And so he would get to a mud pit, he would stop and put it in 4 low at first and start to crawl. I'm like, no, Brian, it's not a tank. It's not how to do it with a Jeep. It is second, wide open, right? Yeah, so simple. All right, so does that make some sense what we're kind of getting to there? The graphic of it. So you got pressure. So here I've got atmospheric pressure pushing down. This is how we measure atmospheric pressure. You probably hear about pressure rising or falling during storms, stuff like that. This is how we measure it. Units, though. I say there are 5 pressure units. What's that mean? 5 pressure units. You're sitting at 5 pressure units. Does that hurt? What do I need to know? Yep, 5 watts. Depends, right? If you're at 5 atmospheres of pressure, you're in extreme pain. Okay? If you're at 5 pascals of pressure, you will probably explode from the difference in pressure inside you because that's so little. That's a vacuum. So I can get to 5 pascals with one of my instruments upstairs right now. Inside the mass spec, we can get down to 5 pascals. But it would definitely explode you if you were in it. So it depends on the units, right? So force is mass times acceleration. We measure it. Now this is the typical physics unit. Is a pascal, okay? And it is. Y'all look for weird things that show up in my slides and point them out. Sometimes it might mean something. The triple equal is not an accident. It's on purpose. The triple equal means is defined as. Okay. So 1 pascal PA is defined as 1 Newton, but that's the force, the Newton, divided by 1 square meter. So 1 Newton of force distributed across a whole square meter gives you 1 pascal. And that's not very much force over that much area. More commonly, we will use atmospheres of pressure. 1 atmosphere, which, again, triple equal, an atmosphere is defined as 760 millimeters of mercury, and that is equal to 760 torr. Okay, now let me back up a little bit and talk about this triple equal and how it affects sig figs. Does anybody know where I'm going to go with this one? Anybody remember the definitions on them and how they affect sig figs? Okay. If you're converting 1.23 atmospheres, right, into, let's say, millimeters of mercury, right? Well, let's say it's 1.234. So that's 4 sigs, right? And we're going to convert it to millimeters of mercury. How many sigs will my answer have? Yes, that's true. Why?
Exactly.
Exactly. Okay, so the 1 doesn't matter, and the 3 sigs on the 760 don't matter. This is a definition, so it's a precise conversion. It is exact. Exact numbers do not affect your sig figs. This is not an exact one, so this one does affect your sig figs. Right, so this one, if we're going to torr, you have to round it off to 3 sigs. Make sense? All right, cool. One atmosphere is also equal to 101,325 pascals, or about 101 kPas, kilopascals. That's probably more common now than the torr measurement. They're using weather now. Weather reporting. Use something that's about 30 Isn't 30 like normal? But I don't know what the units are for that. One bar, I mean, this is unfortunate, y'all. It's a bad thing in chemistry. I don't know that it's ever going to be the case. These two units. So 1 atmosphere is almost like 1 bar of pressure, but 1 atmosphere is 101 kPa. 1 bar is 100 kPa. That's an unfortunate, it's just an old unit that we haven't gotten rid of, and it's going to hang around for a while. And it causes problems. Papers get published, and then there was little errors in the paper, and this can be the why right here. Oh, note here. If I were making a cheat sheet for exam 1, these would all be on, just in case, right? I don't want that to screw up anybody. All right? Thoughts before we continue? Tell me. Nothing yet? All right. So I spend a lot of time at the beginning of Chem 1 on this law versus theory idea. Somebody not in my Chem 1, tell me how you would make a distinction between the idea of a scientific law versus a scientific theory. What do you think? Tell me your name again, because I don't remember it yet.
Right.
Right? Okay, tell me what you think, right?
Law versus theory.
So like, this is going to be the gas laws, right? Not the gas theories, although we'll get to some of that. So what does that mean?
Would it not just be like something that's like proven to be like true?
So that is a very common thought, but I will tell you that if I'm being a true scientist, nothing is ever proven. Math, yes. In math, y'all prove things. In science, we just get a hell of a lot of evidence. Okay? But nothing should ever get to the point where we say, this is now unquestionable. That's not science. We should be willing to question everything. Right? But I still think gas laws has another usage. Law versus a theory. What else? Other ideas? Any other ideas for what it could be with the difference we think?
Why do they exist?
Okay, could be, but that's not the usage, it's not the technical usage of the term. All right, let's think about gravity. Law of gravity, right? What's going to happen if I drop this array? How fast is it going to accelerate? 9.8 meters per second squared, right? At least on Earth at close to the surface, right? If it's not a very significant distance. So the mathematics of how much this accelerates, right? What it's going to do. That's the law of gravity. Why does it do that? Why does this? Why does it? Why does it? You don't know why it does that? Are you sure you don't? That's okay. No one else does either. The theory of gravity is the why, and we're still working on it. And there's a major fight going on about why does it do this. I tend to lean on Einstein's idea with the curved space-time continuum, but that's not universally accepted. Other folks have other reasonings behind it, and we fight about it. Why do things accelerate the way they do? Right? So what it does, the math, that's the law of gravity. Theory of gravity, the why, that's a hell of a lot harder. Does that make sense? So I will claim that nothing is ever proven. So like a theory never becomes a law. They're just totally different things. A law only tells you what the math says. We graph it and it looks like this. The theory tries to explain why it does things. Okay? Does that make sense? What the difference I'm trying to make there? All right. So then Has anybody heard of that term I have in quotes up there? Empirical. A lot of times it's said with the empirical gas laws. Does anybody know what the word empirical means? Thoughts? So, all right, here's how we use it. Empirical formulas just mean, hell, I don't know why it did that, but I graphed it and that's what it is. Okay, so that when you hear empirical laws, that's what that means is, I have no clue, but that's what it did. That's the math. Does that make sense? Okay, so when we're talking about the empirical gas laws, the laws themselves are not trying to explain the why. It's, well, I don't know, but that's what it did. Okay, that's how chemistry really started. I have a beautiful chemistry book at the house. And it's not really that old. It's 1920s, right? But it's talking about some chemistry texts are getting ahead of themselves and dealing with some of these radical ideas in chemistry. In this textbook, we're not going to be dealing with radical ideas like electrons. Obviously, that's accepted now, right? But 100 years ago, it wasn't yet, right? So they were just dealing with the empirical studies. Like, look, well, I don't know why, but if you compress the gas, it does this. If you heat the gas, it does this. Don't care about why. That's where chemistry got its start. And so that's why this is part of chemistry, is you still have it instead of giving it this for some reason. Okay, how many of you have seen the gas laws before? Charles' law, Boyle's law, Gay-Lussac law, Charles Boyle's, Gay-Lussac, Hamilton's, what are the other ones? Obviously combined gas law, but there's another name that I'm missing. Oh, it's probably in here. Hey, who's seen those in high school before? Who's seen this? Yes? Give me hands. I want kind of a looking, Alice, what do you think about a quarter-ish? Okay. All right, cool. What do you remember about it? Was it painful, easy, somewhere in between, what? Middle ground? Yeah? All right, tell me about it. Can you give me any more crunchy detail? What do you think? Plugging it into the formula? Yeah, there's just gonna be a bunch of the formulas to plug it into. So a lot of this section, this lecture is gonna be algebra and rearranging, playing with the different formulas and stuff like that. Okay, Charles's law is the volume of a given amount of gas is directly proportional to its temperature on the Kelvin scale when the pressure is held constant. What the hell did that guy just say? Right? Come on, unpack that for me. What is it even trying to say? This statement of Charles's law. Let's unpack the pieces of it. Remember that in empirical laws, we're not trying to explain the line, right? Just watch it and see what happens. So what are we watching? What are we measuring probably here? Say again? Okay, so we got a way to measure volume, and we can decide that the volume of wait, now this is the thing, given amount of gas, what does that mean? How can you tell an amount? If it's not volume, apparently it's something different. What do you think? How would you tell me how much stuff there is if you can't use volume as a
Density.
It could be related to density. So when you put fuel in your vehicle, what do you measure it usually? Gallons here in the U.S. and liters overseas usually. But I was Navy, right? And the ships use so much more fuel. We do not measure it in gallons. That would be silly large numbers, right? So we'll measure it in tons, right? It's totally different. It's not volume, it's what? What a ton is measuring. Yeah, technically it's force. You could have said mass, and I would have given you that, but technically it is weight. But you can also do it, especially in chemistry, the way we're going to measure amount usually is moles. So moles is the key, all right? So we're going to get to that. Keep that moles thing in your head. So for a given number of moles, she says we're measuring the volume, right? And it's going to do what? The volume of a given amount of gas is, what is that next piece? Is directly proportional to, what's the mass speak mean here? Nope, it's not defined as, okay, good one. What else? Is directly proportional to, what did that mean in algebra class? Yeah, okay, something about the same. So what it means is, as temperature goes up, volume goes up. They're directly proportional, as opposed to being inversely proportional, where when one goes up, the other goes down. Okay, so this says directly proportional. One goes up, the other goes up, and there's some more usage of the term here where we're going to think that that increase is also linear. So a lot of chemistry is y equals mx plus b. Remember that from algebra, y equals mx plus b. Okay, and so a lot of this is, if I plot volume, that's my y, right? And temperature is my x. It claims that there is a slope, m, and directly means that the slope is a positive number. As temperature goes up, so does volume. Okay, so we're going to be graphing these a lot, especially in the lab coming next week. Okay, next Monday's lab, we're going to be graphing a lot of these things. So I want you to get used to the lab quest, the little logger thing, Monday, so that we do it again Monday. Yes, ma'am.
For example, if you heat up like water.
Why? So, all right, let's look at this for a second. Here, I've got Miriam's beaker full of water, okay? How much water do you want to put in there? We use volume because it's liquid, right? So let's say that we've got 1 liter of water, okay? And over here, Braden has a balloon, I guess the entire balloon on, right? Of 1 liter of gas, okay? All right, you both heat this up significantly, all right? You apply a lot of heat. You probably don't want to apply fire to the balloon. It's not usually good for balloons, but we'll heat it up somehow, okay? Come back to it after you've heated it up. Do volume versus temperature, right? Does that make sense? So here's where we started at whatever, this is 1 liter right here, right? And so, what temperature did you start at here? Pick something. 75, so let's do like 250K. Still your 75C, I'm just converting it to K, all right? K is gonna matter. So 250K, right? And then we're gonna heat it up by like 25C, so we've got a 275K. What does this do? If I graph this, what's it gonna do? It's not, it's liquid. So even if we're not boiling yet, right? Because we're only about 25, right? So flatline. Doesn't really change. Now, in physics, if you're taking upper level physics, you'll see that that's not technically true for liquids or solids, but we're going to act like it's true for liquids and solids here because the change is very, very, very minor. Do I have any engineering majors? Okay. Volume, there's a coefficient of volumetric expansion beta and a coefficient of solid expansion. I forget what they use for it. And if you're designing the bridge, it matters. Okay, but if we're measuring a liter of water, it does not matter. Okay, so I'm not telling you the truth here. I'm just making a simplification that the water essentially doesn't change. Okay, but Braden's balloon here Does change significantly, okay? So his y equals mx plus b. M is not 0, and in fact is greater than 0. It's positive. Slope is going up, okay? Right? It's in blue, right? Yeah. Yeah, we have to have something we can measure, right, to see. Yeah. Make sense? That's where we're gonna go with this. Play with all this. Told you, I warned you, all those times in algebra class, when am I ever gonna need this? Okay. All right, cool so far? An idea here? You go ahead, I think I've got the graph on here. Okay. So my graphic, notice that it's linear, okay? And again, engineering wise, it's linear until it isn't. Okay, all right. All right, thoughts on this? I'm gonna come back to the equation at the bottom first. I want you to process the graph and the linearity and stuff like that first. Where are we at with? Question, please give me questions. You gotta use your words. Oh, did we talk about the idea of setting up a back channel? How are y'all communicating so far? Yes, email. So Bella set up, and Blake did it before. Blake got a lot of usage out of it. When he did it for me, he set up, I think it was a Discord, but I'm not positive of that, and got everybody into it, because some people are a little less aggressive than I am, imagine that. And so they would be willing to send him a question on the Discord, and then he would ask it for them. So that might be a thing, is if y'all do set up a Discord for the class, you can set one up without me in it, and then we have to talk about it, right? And they can feel free to tell you stuff like, you would do that too fast, or something like that, okay? So I would recommend doing something so that, now I would love for y'all to just feel comfortable enough to stop me and ask me things, make me clarify things, okay? Remember, you don't pay me, okay? I like you heard me. Okay. So, this part gonna make sense for you so far? Linearity idea? Okay, now I'm gonna come down here to this one. Probably what you saw more in high school. V1 over T1 equals V2 over T2, right? That's probably all they gave you, and then they just glossed over it, and all this other stuff is underlying all that, right? So we gotta get a little deeper now at high school level, okay? But this is the basic math of this that makes it work, okay? Yeah? That's what I would have on my formula sheet. Allison, what are your thoughts?
Yeah, I agree. It's just knowing that relationship between them, that as you increase temperature, it will increase the volume.
It's a good point.
Just know that relationship well. Know the other relationships that we put.
Yeah. And think about your problem. When you're working your problem, right? And you have 2 liters of gas and you heat it up and your answer says 1.5 liters, go back and check your math. You did something wrong. Because if it's gas, it should increase, not decrease. When you heat. Yeah, it's a good point. Knowing that. Yeah.
Real world examples like having a balloon and, placing it in the freezer, the volume decreases, you can kind of visualize that.
Yeah. All right, everybody got the formula? We're about to try it. Next screen is going to be a practice question. Good? V1 over T1 equals V2 over T2. Okay. Oh, wait, before we go to that. You're going to want that also. You're going to use this so much that you're not going to need it on your formula sheet. It's going to be automatic. But do all of this gas law stuff in Kelvin, not in C. All right? Hopefully you did see what Kelvin is back in Chem 1, right? Y'all know what it is? Y'all remember? What is Kelvin? Cool. Okay, no, it's not there. Alice, you tell me if I'm just misreading. Do you think it's there? Do I need to spend some time? I think I think about that, but I might be misreading. Yeah, I think so, but do y'all really, or do I need to spend class time on what Kelvin is, because it's extremely important.
the most like, what's your way of explaining what Kelvin is, and maybe he can build off of what you have to say about it. And if it's just a basic definition, that's fine. You need to build off of something.
Say again. It is a form of measuring, that's just a units thing, where the scale is set up. All right. What's the warmest temperature you have experienced, Mary? Oh, you're having to convert, I'm sorry, yeah. What about 32, 33? Yeah. Are you thinking in C? Are you thinking in Fahrenheit? Okay. Oh, really? That's the warmest you've seen? Okay. Yeah, okay, good. The warmest I've experienced over the Persian Gulf was 135. It was brutal. Oh, anybody see more than that? What's the coldest you experienced? 20? Really? That's cold as it's gotten for you. You what? -5 Fahrenheit, I assume, right? Okay, all right, so you're gonna get some -5C next week, right? But okay, let's think about 0 Fahrenheit, 0 degrees Fahrenheit, right? Or 100 degrees. Why did we pick where those are? Why are those where they are? Yeah. Say again? That's true for Celsius. That is exactly why we did it for C. 0 C is where water freezes, 100 C is where water boils, and it makes sense, right? Fahrenheit, why is 0 F where it is, and why is 100 F where it is? No one really knows. One story that I like, but I certainly cannot verify this, but one story is I like is that it was the Brits, right? And that they just decided these are the temperatures we need. And it turns out that they were pretty close, that 0 is almost the record low temperature in London, and 100 is almost the record high temperature in London. So it might be based on the temperature in London. Sounds like a thing that the Brits would do also, right? So like, I know everybody has to use ours, right? So I don't know if that's really true or not. It's just a story that I heard. I think it's kind of cool that way. Okay, but Owen's right about Celsius. At least we made it make a little more sense. C, right? But what does temperature mean? What is temperature? Ever thought about that? What is temperature? Never thought about it. Just take it just like, okay, it's temperature. I don't know. Okay. It has to do with average kinetic energy, and it's how fast the particles are moving, right? So you have high temperature, you have really, really fast moving particles, right? But as you start to cool them down, they start to slow. Does that make sense? Okay? And if you slow them down enough, what? Stop. Wait, what would negative mean? If they're just vibrating, what would negative mean? You can't vibrate negative. So what would it even mean? It does not have a meaning. So negative amount of vibration has no meaning. That's K. So Celsius, we just take it at water, freezing and boiling, right? But then Lord Kelvin, this is another Brit, talks about, well, no, there's an absolute scale. If it's amount of bouncing around of the particles, right? If you slow it down, there is an absolute zero. There's a spot where they stop moving, and you cannot go any older than that because there's slower and slower moving until there's not moving, and there's no negative. Negative is not a thing. So that's the Kelvin side. And that's actually what makes this math work, is when you do it in Kelvin. It does not work if you do it in C. Gotta use Kelvins. Okay, so to convert from C to Kelvins is easy. Add 273.15. Convert from Fahrenheit, no, you've got fractions, 5/9 or 9/5 or whatever. Don't worry about it, I'm not gonna use S, okay? So you convert from Celsius to Kelvin, add 273, or if you need, for some reason, to go from Kelvin back to Celsius, subtract 273. Go in, okay? Good? All right, practice question. Go. And remember, like Monday, I highly encourage you all to work together if you want to. Nice and easy, y'all? Can I just double it? Look, I doubled the temperature, right? I went from 30 C to 60 C, so could I just double the volume? Take a shortcut? Trick. What's the Admiral Akbar from Star Wars? It's track. No, cannot just double it. Why? Right, I did not double my temperature. I only changed it by 30 K. Yes.
Is it degrees K or just K?
Oh, good question. Technically, it is just K, and technically it would be the little degree symbol with C, and y'all, it's going away. Most people don't even do it anymore. They'll just write 30C and not worry about the degree symbol. I certainly do not worry about it. But with K, it's officially just 30K or whatever. This is 303 K. Everybody feel confident with it? Work it out. He's there. He's almost there. You use that formula? Okay. What'd you plug in here? Oh, you didn't, right? Okay. Then the two temperatures go. All right, cool. Yeah. This. Okay. All right. K's cancel. Don't forget you're using canceling, right? So when I did this, I went ahead and set it up so that I'm canceling my K's. That helps me make sure that I'm getting the right answer. If you give me, anybody on a physics course right now? Okay, let's say physics 2, right? You hand me a random problem from physics 2 without me studying for it. If I took like your final exam, like a multiple choice final exam from physics 2, I would get more right than I should because of that trick right there. Just doing the dimensional and just doing the unit canceling is the best trick in all of science. You'll accidentally get things right if you just do the unit canceling. Okay. I got 136 mils. Yeah, happiness? All right, good. Next one. So that was Charles's law. This is Gay-Lussac or Amundsen law. Variation of gas pressure, constant volume. So this time we don't have a balloon. This time we have a pressure vessel that cannot expand. So the volume is locked. Okay? So it wants to expand though. So if this were a balloon, if you're heating it up, the balloon would be expanding, right? But since we're not letting it expand, instead the pressure inside it, if we have a pressure probe, which we do have upstairs and we'll use Monday, right? That you can see the pressure go up. Does that make sense? So, the pressure we get in on the gas is directly proportional to its temperature on the Kelvin scale and the volume itself. All right, unpack the science speak again. What is he saying here? What are those words? How would you rephrase this law for you?
It's the same one. It's the same principle.
Same principle?
So you just change the volume for pressure.
Good. And so the equation looks similar, right? So this one just says, as temperature goes up, so does pressure, that it is proportional to it. Okay? So it is some constant, some m, my slope here, times the temperature. Ready for a practice problem on that? Oh, still in Kelvin. There's your practice problem. Now it's going to be really similar here. Yes. Oh, yeah, yeah. That's probably the one you want to solve the problem. This, of course, still matters. These are really restatements of that kind. Good on?
Yeah, is it not just the same?
It is the same setup. It's just instead of it being V1 over V2, I mean V1 over T1, V2 over T2. V1 over V1. V2 over T2. It is the same, you're right, it is the same form, yes. And it will work the same way. I think I gave you a twist in the problem, right? But it did. Oh, I saw it. So then, use information. What I throw at you here that you do not need?
Volume.
That numeric volume, right? Because the volume stays constant. So it's still 543.2 mils at the end of the problem. Okay? I am rushing this, and that's on purpose, y'all. We have so much to cover today. But you set it up the same way, plug it in and solve. Yeah. I got 1.47 atmospheres. Okay, Boyle's law, and this is the third one that's usually seen in high school level. Boyle's law says the volume of a given amount of gas held at a constant temperature this time is inversely proportional to the pressure under which it is measured. If you have a heat pump at home, or if you like use an air conditioner in your car during the summer, this is the pressure that makes it. This is the principle that makes it work. This is how a lot of heating, cooling, how your refrigerator keeps your food cold. This principle right here about pressurizing and depressurizing the gas. What's different? What's different about the wording? Yeah, so wait a minute. So when I said directly proportional, I said that if, for the first one, right, if the temperature goes up, the volume goes up. Or for the second one, if the temperature goes up, the pressure goes up. This time, something new. Now, what am I saying?
You increase the pressure.
The volume does not go up, it goes down. This is going to be important. This is what it looks like in the graph The graph is going to be really different this time. Graph here. Okay. Graph is going to look like this. All right. So you remember from algebra, do you remember doing those different shapes, like the y equals x, the linear graph versus quadratic versus what else did you do? Probably square root, and this should have been one of them also. Y equals 1 over x should be this. Of course, it's just first quadrant. But. So, a lot of times we like to have linear functions on our graph so that we can use y equals mx plus b. As much as you might have hated y equals mx plus b in high school algebra, I promise it is the easier version than trying to solve for parameters on a quadratic or something else, okay? So we like to do a thing called linearize our data. So what I've done here is I've taken the same data, but on my y-axis, instead of plotting pressure, I am plotting the inverse. I'm plotting 1 over pressure. When you do that, look at what this graph does. That curve, 1 over x, becomes a nice linear function. Okay? So that's the process called linearizing your data. We'll do that for Monday's lab also, is linearize your data. That way we can use the y equals mx plus b. Okay, so P1, B1 equals P2, B2, right? The math on this one can actually be easier though, right? So what would I do? I'm going to use that formula, right? And so the algebra-ing is going to be a little easier, right? I use algebra-ing as a verb. Okay. All right, so I'm going to plug them in, right? And so now how am I going to solve for V2 over there? Just combine both sides together. Beautiful. So it can actually be a little easier sometimes. Sometimes it's not. I got 11.3 atmospheres. I know I went through that really quickly. Just go back and check it later. Make sure that you're good. Of course, I put it in the homework too. Okay. Good so far. Yes? All right. So let's see. The Gay-Lussac law said that if volume is held constant, right, and you increase temperature, then pressure increases. Does that seem unrealistic? See? Does it seem like it would be a hard experiment to set up? Like, how would you do that? How would you set up this process to see that the Gay-Lussac law where we hold volume constant and increase temperature and measure pressure? How would you do that? How do you combine it like that? That's the problem, right? Is combining it. So, turns out, sometimes you can't hold everything constant except for two things, and we let multiple things float. We have this combined gas law. So this next one, combined gas law, we're going to staple those together, right? So we had P1 over T1 equals P2 over T2. We also had V1 over T1 equals V2 over T2, right? And we had P1, and we had P1 V1 equals P2 V2, right? Well, if you just staple all those things together, we get this combined gas law, right? And so, really, this kind of takes care of it for you. Makes sense? It kind of combines all three of those stuff. Good so far? Well, all right, so I was talking about not being able to hold maybe the volume constant or something, right? But now I've got volume, temperature, and pressure. Cool, everything is great now, right? What could go wrong? What could possibly go wrong with my setup? That's got all three of those things, right? So everything's good, yes? What could possibly go wrong? You think of anything? What could throw a wrench in my problem here? Yeah, but, what would cause that problem? You don't know. Oh no! What if I have more gas? Actually, more moles of gas than I had. Now all bets are off, right? So that changes everything. So we have a new version. This is one I actually use all the time. PD equals nRT. How many of you seen ideal gas law before? Yeah, a few. All right. This one, honestly, this is the one I use for everything. I don't use Boyle's law or any of those. Just this one. So then I only have to memorize one thing. PD equals nRT. It still does. PD equals nRT regardless of what you do well. Almost regardless. Right? Pressure, volume, temperature, but now this N is my number of moles. Okay. Also R is the universal gas constant, and it is one of those super constant things. We think that everywhere, when in the universe, except there is an argument that maybe right at the Big Bang, maybe a couple of microseconds, if that long, maybe not that long, after, that R could have been fluctuating. But for the most part, R does not fluctuate, right? So if you measure the universal gas constant right here on Earth, right, and you can go back in a time machine and measure the universal gas constant in London with newtons, right? Same gas constant, same values, right? Or far in the future on some other planet that we've not discovered yet, R still R. Or in the center of the sun, under extreme heat and temperature, R is still R. Same numeric value. And that's one of the keys to solving these problems, because R is rock solid. Doesn't change. Unfortunately, my students then balk when I put this up, and they're like, well, wait a minute, you just said it doesn't change. Those are not different. They are just in different units. Okay? That's why the values look different. 1.987 calories per K per mole is exactly the same as 8.314 joules per mole K. It's just in different units. Okay, these are all the same R's, measured in different units. Okay, Allison, which ones do I tend to use?
I've seen most of the second one.
Yeah, that one you use in P-Chem all the time, right? And we'll use that some, especially in the thermodynamics section. I think for this section, we'll probably use this one most, but I'm not sure of that. I'll probably hardly ever use that. And I hate bars, but sometimes they sneak in, right? I would put all these on my cheat sheet just in case, but to be honest, I will probably use this one most in this unit, and the top one we'll use a lot in the last unit. Okay? But they are the same. Also, I give you a website here for where you get the quote official values. This is National Institute of Standards and Technology. These are the guys that there are jobs there, and that's what you do is you work all day trying to figure out, or maybe all decade, trying to figure out one precise value. That's where you go to get these. All right, algebra time. So this is how it really works. Solve for your unknowns, okay? So please get really comfortable with all of the algebra stuff and moving things around, shenanigans, where you move all your stuff around. So the ideal gas law can be more powerful than any of the other gas laws that we've talked about today. because you can rearrange it this way. Divide both sides by NT. Now I have PV over NT is equal to R, and we know that R does not change. So the R at the beginning of your experiment is still true as the R at the end of your experiment. And so PV equals PV over NT starting has to still be equal to PV over NT ending. Each value, the pressure might have changed, the volume might have changed, the moles might have changed, but that expression PV over NT still got to come out to the same value. Still got to be R. Okay? So R is always equal to R, so you can rearrange it this way. P1 over B1, or P1 B1 over N1 over T1. Syntax is not working. Try that again. P1 B1 over N1 T1 is always going to be equal to P2 B2 over N2 T2. Equals P3 B3 over N3 T3, right? Good math. It's always got to come out with the same R value, because R is always the same. Make sense? All right. Any chemistry majors, we hope, right? Cindy? So, unfortunately, ideal gas law doesn't always work. And so I would be remiss if I didn't tell you about this is coming later. We do not need this for this course. I'm only previewing it for my chemistry people, maybe my engineering people. This is ideal gas law. Sometimes gases start to behave non-ideal version. And this is one of the non-ideal gas laws that starts to correct for volumes and other values. This is molecular attraction term and stuff like that. So later, that's coming where it starts to change in a non-ideal. Now you get that in PChem. This is the issue. The first one, I think it's PChem. Yes. All right. How are we feeling on the homework from last time? I was really happy that it was all in and that was good. How are we feeling on the lab? Writing up that stuff. Does that feel opaque to you? Feel like you know what I'm looking for yet? Maybe? Any questions? All right. Or let me ask a different question. Has anybody started yet? Okay, well, that's when the questions will start coming up. Okay, don't wait. When's it due? Midnight when? I think that's right. Okay, look, y'all, please don't wait to start it. First, make sure you've got contact with the rest of your lab partners. There's a lot to do on this, so you need to have started by now, really. But you need to be talking to each other and trying to figure out how are we going to fill in the parts of this lab, okay? What do we need to do? And let me know and let Allison know if we can help you with this, okay? Please do. Huh? No, I put that in. There are slides after this, y'all. Y'all one more? Okay, just one more. I was just working through an old homework that somebody had. I recycle these slides semester to semester. That's all it is. So if you see extra stuff out there, don't. Miriam is right. Don't hesitate to ask me about it because sometimes I screw things up. All right. See you on Monday. If you don't have any questions, I will be here for a while today, and I will be here all day. I'll go out all day tomorrow. I have to be here for a class starting at 8 in the morning. Let me remind you about the other class tomorrow night. So remember that my class tomorrow night, I got to go through all the syllabus stuff and stuff like I did with y'all, but then we'll get into the actual work side. Y'all are always welcome to come Thursday evenings at
5 o'clock, and it's right across the hall.
Yeah, and so that's where we'll work on the homework, so if you need extra help with it, okay? Oral labs, do that too, okay?
Oh, yeah, and by the way, SI sessions, tutoring stuff for people start next week. Those times are Tuesdays and Thursdays from 2 to 3:15. I'll send out some information in like a mass email. So if you have any questions, just respond to my email separately because it doesn't work for your respond directly to that message. But, I haven't got the location yet, but I will let y'all know as soon as I do. And, maybe next time I can do like a demo on how to run 2 group sessions with me if y'all want to do that, because I have more availability.
Well, did you get a spot for your, that's fine. You did get to a seven? Correction, not next Monday, y'all. Next Monday's a holiday. So I'll see y'all. Yeah. Well, we'll have a quiz next time we have one. Oh, yeah.
We figured out what we wanted. It's, absorption versus absorption with, oil lamps on here.
All right, we'll talk about it, yeah, it's cool.
But it's, I don't really have anything for it.
Well, it does, when you say basis, it makes it perfect. The green units that are on there. It also smells like it's nice set up as a fundamental start.
Okay,
All right.
It's not for y'all.
Lots of questions.
All right.
So,
If y'all wanna come.
before I get to this,
Okay.
I turned in,
You said it. One person did.
yes, it was it was a document, but I pasted like pictures because I had to do it live.
Oh, okay, look and see if you can see my response. You got your, George, I was wondering if you could see my response.
So I'll start my tutoring stuff up next week, so you think I'll have the schedule. But it's just start next week, so I can't do tutoring like tomorrow. But,
It's not happening.
yeah, so we can.
Oh, I thought you got that. Not first. Okay, go there, assignments.
You can look out as much as you want, you know, if you want to just try one appointment, see how it goes, and if it helps you. Maybe you can someone else has a better perspective, that's totally fine. So I guess do whatever you think you should do, like, do the thing, just see how it goes, see how it helps. It's, some people learn better.
Because I knew I couldn't upload the images directly from my phone. So what I did is I emailed them without state email, and then I copied them from the email and pasted them on the document.
Just making my comments. Allison, do you know how they see the comments that I put on?
On the assignments,
Yeah.
I mean, usually you can just click on, like, see. Oh, it's like sometimes I've had this before. But it doesn't always.
They should tell me when it doesn't matter, so I don't bother fighting. Yeah. Anyway, that's fine, what you just, you can continue to do it that way, which, if it's easy.
Also, you do the cave stuff, right?
Yeah.
How bad?
Let's see, the last we went was, when Patty John's, I guess, a week ago yesterday. Ben? Yeah. We don't have a camping trip planned yet. I'm trying to get Allison. But get with so Bella that stuck her head in, look for her, Human Honor Society. If they set one up, they'll be the crew. What's your major?
Biology, but
Did Taylor graduated, didn't
yeah,
he? Because he was really wanting to go, so I was wondering if y'all would be involved.
yeah, I wanted to do gynecology. You told me.
I know Taylor. Excellent. So what do you know about Reeves?
Reefs? Not a lot. I mean, I know they're endangered.
That's mine.
So,
There were reef systems. They kind of died out in a certain era. Era that definitely reached out. And then much later, Permian period, you got fish, right? But the Mississippian is right after the Permians, talking 300 plus years ago. There's corals, structures. Ooh, yeah. So you can look up Mississippi and reef systems. There are a couple of reports out of Denmark, I think, something like that.
Huh?
Yeah. Well, that's awesome. Yeah, so I'll totally nerd out on the paleo side too. Is this yours?